Okay, the following is a video over three notes, and these are derivative rules. Before we would do the limit definition of a derivative, and you can always do that. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. However, there are certain problems where this would be very difficult to do if you had certain functions. This would take you a very long time. So we have some rules that we're going to learn. Okay. So remember, I do want to do a quick review over notation. If I have a function f of x, okay, if I want to find its derivative, then I do this. I do d dx of f of x, and this gives me f prime of x, which could also be written as y prime, which could also be written as dy dx. Okay, remember, these are nouns. Okay, these are the derivatives. All right, these are the derivatives. Okay, in this thing right here, this d dx, this is an action. Okay, this is a verb. This means that I am taking the derivative. Okay, so I'm going to start using this notation now to show you how this all works. Okay, so let's talk about our very first rule. Okay, and this is the constant. Oh, not the constant multiple rule, just the constant rule. Okay, go ahead and you can get rid of that. It's not right. Okay, hold on. Okay, here we go. Okay, this is the constant rule, not the constant multiple rule. And what this says that if c is a real number, then if I take the derivative, taking the derivative of a number, I get 0. Okay, so an example of this would be like, okay, if I take d dx of some constant like 3, then I get 0. Okay, and you're probably going, okay, what are you doing? What are you talking about? Well, let's think about what a derivative is. A derivative is a function that generates a slope of the tangent line at any x value. So real quick, if I just draw a graph, okay, and I have the function f of x is equal to 3, then at 3, 1, 2, 3, okay, that's a horizontal line through 3. Okay, this is the function f of x equals 3. It's a constant function. Okay, this is my x-axis, this is my y-axis. Now, the question is, remember, derivative also is another way for you to kind of say slope. Okay, what's the slope of this line? What's the slope here? The slope is 0, meaning the derivative is 0. So if I do this for any number, I get 0. So if I take the derivative with respect to x of, say, some number like 72, okay, I'm going to get 0. If I take the derivative with respect to x of the number pi is a number, not a variable, folks, going to give me 0. Okay, so we can quickly just take a derivative of a constant and get 0. All right? All right, let's take a look at the next rule, the power rule. This is one of my favorite rules. And so here's what it says. Okay, it says if n is a positive integer, then if I take the derivative d dx of x to the n, then I get n times x to the n minus 1 power. All right, so let's kind of think about this for a second. If you remember, and I'm just going to write out a couple of examples here. If I took the derivative with respect to x of the function, say, x cubed, all right, if I took the derivative here, and you've probably seen me do this, but I get the derivative 3x squared, okay? And you're probably wondering, okay, how do I do that? Well, I take my exponent, all right, and I drop this exponent out front and multiply it. So I get 3 times x, and then I subtract 1 from my exponent, okay? And so then I get this. I get 3 times x squared as my derivative, okay? If I took let me do another example. If I took the derivative with respect to x of, say, no, I don't know, x to the 4th, okay, then that's going to give me, okay, I'm going to drop the 4 down, all right, and so I get 4 times x to the 4 minus 1 power, which just gives me 4x cubed, okay, and that's my derivative, all right. So this is something that we're going to do a lot of. okay? And it might not always be positive numbers. They could be negative numbers. They could be fractions. So the power rule is a very, very useful rule, and we'll do a bunch of practice problems that involve that, okay? All right, the next one, the constant multiple rule. All right, well, let's take that. Let's do, let me do another example here real quick. And before I do that, the one thing that we've got going on here is we have some constant c. Now, when it says c is a constant, okay, that means that c is a number, okay? That's what c is, okay? And so if I were to, if I had some number being multiplied by some function, what I can do is I can pull that number out front and then multiply it by the derivative, all right? So let's think of an example here. Let's say that I'm taking the derivative with respect to x, and let's just do 3x squared, okay? Now, I could rewrite this because I have a constant multiple. I'm multiplying the function x squared by 3. Okay, if I have a number that's being multiplied out front, I can pull that number out and multiply it by the derivative. So I can take 3 times d dx of x squared. Okay, now I can take this derivative using the power rule, and I end up getting this. I end up getting 3 times, let me do the derivative here, 2 times x to the 2 minus 1 power. All right, and if I do that, then I'm just going to get 6x to the 2 minus 1 power, which then just gives me 6x to the first, which just gives me 6x. Okay, so sometimes when you do this, if you just do the power rule on this, you just, 3 times 2x to the first, 6x. Okay, you can do this pretty quickly. I can draw this out into steps and really show you this rule, the constant multiple rule. Using it on the power rule, guys, isn't terribly effective. You can show it that way, but further down the line, when our functions get very, very complicated, pulling this number out front will save us a lot of headache and a lot of computation that goes on in between. So sometimes this is very useful, sometimes it's not, okay? It just kind of depends. But the rule is there for us to use, okay? So let's go ahead and take a look at another one, okay? All right, and this says that if f and g are differentiable at x, then if I take the derivative of the sum of two functions, then I can just add their derivatives. Okay, so let's look at an example here. All right, so the example I would use, let's just do this. Let's just take the derivative with respect to x of, say, I'm just going to make a few things up. I'm going to do 4x cubed plus 7x to the 6th minus, and it's a sum and difference, so it works for both, sum and difference. And then minus, say, I don't know, 3x to the 5th. All right, I'm just making this up. Okay, so what I can do here is I could take the derivative of each individual one of these, okay? And I could do d dx of 4x cubed plus d dx of 7x to the 6th plus, I'm sorry, minus, all right, hold on, 7x to the 6th minus d dx of 3x to the 5th. Okay, in all of these we have constant multiples. We could pull those out. I'm not going to do that in this case. I'm just going to take the derivative of each individual one of them, and so I'm going to end up getting 12x squared. Okay, bring the 3 down, multiply by 4, it gets 12. 3 minus 1 gives me 2. Plus 6 times 7 gives me 42 x to the 5th. Okay, and then minus 5 times 3 gives me 15x to the 4th. Okay, and that's my derivative. All right, that's it. So, but I can do this another way. You don't have to separate all of these out. Okay, if I wanted to do, let me do another example. Let me just do like d dx of like, I don't know, 3x squared plus 4x to the 5th minus 6x to the 3rd. Okay, who knows? All right, I can just do these individually. I don't have to write out this step. You are more than welcome to write out that step. But we'll get pretty fast at these to the point at which I'm just going to go, okay, this is 6x minus 20x to the 4th minus 18x squared. Okay, and I can kind of just do those in my head. All right, if it requires you to show your work and to really separate things out to do what you're doing on the power rule, then do that. Okay, do what works for you. Okay. All right, let's take a look. All right, this is a unique one. All right, and I will show you how this works in class. But the rule is that if I take the derivative of e to the x, then I just simply get e to the x. All right, so even if I have an example like this, let's say I have d dx of, say, 5 times e to the x, I can bring out that constant multiple, 5 times d dx of e to the x. The derivative of e to the x is just e to the x. So I get 5 times e to the x. Okay, and that's it. All right, so the derivative of e to the x is just the same thing. Okay, that's probably the easiest one. That's one of my favorites. Okay, but then we've got this one. Okay, and I don't have a rule for this necessarily. We did this one. We've done this one before, and I know that my derivative is going to give me 1 over 2 times the square root of x. Okay, but let's look at this a different way. Okay, if I were to take d dx of f of x, okay, that means that I'm taking d dx of the square root of x. Okay, you can do the limit definition on this. However, okay, I want to know if I could use one of my previous rules. Okay, and I'm curious to know how else could I write the square root of x? All right, am I allowed to write this as d dx of x to the 1/2 power? And the answer is yes. Okay, so now I have x raised to an exponent. I can now use the power rule. Okay, and I'll end up getting this. All right, so this is useful for like cube roots or stuff raised to the 5th root, stuff like that. So same thing here. Okay, I'm going to drop down my 1/2, multiply it out front. So 1/2 times x, and that's raised to the 1/2 minus 1 power. Okay, so this is where we got to be able to add and subtract fractions, multiply fractions. Okay, fractions are your friend. They're not going to ditch you on a Friday night. Okay, Pythagoras and fractions and all the math people, they're all here for you. Okay, it's going to be okay. All right, so now I have this. I have 1/2. Let me separate this out. I've got 1/2 times x to the, okay, 1/2 minus 1, 1/2 minus 2 halves ends up giving me 1 minus 2 is negative 1 over 2. Okay, so I have this. And I'm going to separate this out into the product of two numbers, okay? But I have x to the negative 1/2. All right, now for me to get rid of my negative exponent, then I put that down in my denominator, okay? And I've got 1/2 times 1 over x to the 1/2 power, okay? And I can rewrite that as 1/2 times 1 over the square root of x, okay? And I can write that as one fraction and say 1 over 2 times the square root of x. So this is power rule is very, very, very useful. It's a very useful tool for us. We can do a lot with this. We can do negative exponents. We can do all sorts of stuff. Okay, so let's talk about one more thing, and that's higher order derivatives. And basically what I've got here, I'm going to start off with a derivative. Say f of x is equal to, I'm going to do, say, x to the 5th. Okay, if I take the derivative of this, okay, if I take d dx of this, then I get f prime of x is equal to 5x to the 4th. Okay, this has a derivative. Now, the question is, can I take a derivative again? And the answer is yes, okay? And if I take the derivative of a derivative, I get the second derivative, f double prime of x. And I'm just going to take the derivative again, and that's going to give me 20x cubed, okay? And I'm going to take the derivative of this again. And if I take the derivative of f double prime, then I get f triple prime, okay? Let me rewrite that so it looks reasonable. I get f triple prime, okay, of x. Do the power rule again, that's going to end up giving me, what is that, 60x squared, okay? And so then I could take the derivative of this again. All right, if I take the derivative of it again, I get the fourth derivative. Now, it's going to be a point where we run out of room here. So if I write my derivative like this in parentheses, f the fourth derivative, putting this in parentheses does not mean f to the 4th. It means the fourth derivative of x, which is going to give me 120x. Okay, if I take the derivative of this, okay, d dx of that, all right, I'm going to get the fifth derivative of x, which is just going to give me 120. Now, the reason why I got that, I haven't gone over an example. If I have 120x to the first, take 1, multiply it out front, so I get 120 times 1, times x to the 1 minus 1 power, so I get 120 times x to the 0. X to the 0 is always 1, so that's 120, okay? And you can also think of this is a line, 120x, a slope of 120. What's the slope of 120x? 120. Okay, if I take the derivative again, all right, I'm going to get the 6th derivative. Oops. So that's the 6th derivative of x, and the derivative of a constant, you guessed it, folks, is 0. Okay, so it's a lot of information. This is probably one of the most fundamentally important things that we're able to do here. These are the basic derivatives. We'll learn many, many more. But these you need to have memorized. And you need to be able to look at a function and be able to do that and take its derivative. Okay, we have multiple derivatives. They all tell us something different. Okay, so what I want to do, I'm going to go ahead and stop this video and do another one. You guys are doing a wonderful job, but let's go ahead and do the next